Hello everyone, welcome to lecture 3 of week 10 of the course Power Network Analysis, in which we continue with our second last module on fault analysis. In this discussion, we will take up the analysis behind analyzing or understanding the impact of uh, two categories of unbalanced or asymmetric faults. Those would be line to ground fault, also at times known as phase to ground fault, and we'll also take up double line or phase to phase fault. In notion of faults, these line to line or phase to phase, they pertain, they're analogous terms. And then the last category of unsymmetric faults, which is double line ground or phase to ground, we'll be discussing it in the next discussion. So in the previous lecture, we had discussed about Fortescue's theorem and the implication of Fortescue's theorem in decomposing n-phase system, which is assumed to be unbalanced. This can be categorized or decomposed into n-balanced systems. By balanced, I mean that the corresponding phasors, be it voltage or current, the corresponding phasors for a three-phase system N would be equal to N. The voltage magnitudes or the current magnitudes, basically the magnitudes would be equal to each other, and the corresponding phase angle would also, the phase angle difference between these phases would be equal. So for N-phase system, there can be certain combinations of possibilities. One equal phase angle is by default 0 degrees or 0 radians, and the other possibility for a n-phase system is 360 degree by n. For n is equal to 3, this angle turns out to be 120 degrees. For a so basically we can create corresponding balance systems, one with 0 degree as the equal phase angle and two others with 120 degrees phase angle differences between the phasors, either in the clockwise or anti-clockwise direction. For n is equal to 2, the possibility here would be either 0 degrees or 180 degrees. So we can have a zero sequence component present for a two-phase system, and the other sequence component with some name would have these two phasors in opposing fashion to each other. For n is equal to 4, four-phase system, the number of possibilities which can exist would be either 0 degrees or 90 degrees. With 0 degrees, we would have one parallel set of phasors, and with 90 degrees we can have three other combinations of phasor diagrams in which the four balance systems can exist. So we had discussed about n is equal to 3 specifically for the three-phase network, application of Fortescue's theorem, which essentially decomposes the phase components into three balance systems, and that's how we came up with the notion of sequence voltages or currents. We had also discussed about sequence impedances, whose notion is a bit different compared to sequence components of voltage and currents, because these impedances, they pertain to the impedances offered by the corresponding sequence currents in a particular sequence circuit. And we had discussed about the sequence impedances for transmission lines and the three-phase transformers under different possible configurations. So I request the viewers to please revisit the previous lecture. That would give a good premise of what these sequence components would be. Today's discussion will start with sequence networks or components for a synchronous generator. To be specific, we would take the case of loaded as well as unloaded condition. In case the network or generator is unloaded, that would mean that the corresponding currents would all be 0 in an unloaded scenario, which would mean that whatever is the internal EMF generated by this synchronous generator, the same voltages appear as the phase voltages of VA, VB, VC respectively. In case the generator is loaded, these currents won't be 0, and consequently the corresponding phase voltages at terminal won't be same as the internal EMFs. with that premise, we assume our three-phase synchronous generator, which is loaded. For unloaded condition, the currents would simply become zero. We have a three-phase synchronous generator, which is inherently producing a balanced internal voltage. So basically, if EA is a phasor in frequency domain defined as EA at an angle 0 degrees, then EB is EA at an angle minus 120 degrees, and EC would be EA at an angle 120 degrees. Why only this combination of voltage? Reason: synchronous generators inherently by design they produce positive sequence voltage, and that is the reason why this sort of voltage arrangement would come in. For more details, please relook our discussion on synchronous generators, where you would have a better understanding why the stator voltages inherently tend to be positive sequence voltages. So by balanced term here, I mean that the internal EMFs are inherently positive sequence voltages, and the neutral of this generator is grounded through a neutral impedance Zn. Since the generator is feeding in some three-phase load, so that's how the notion or orientation of phase currents have been shown. And if I apply KCL at this neutral point, then the corresponding neutral current has to be an incoming current, because the phase currents are all outgoing currents, they are feeding in some load. So if we try to sort of understand what would be the sequence network or component or corresponding impedance for a loaded synchronous generator, the way we did it for a three-phase balanced load yesterday, that is, we started with the phasor equations and then applied the Fortescue's theorem transformation. On similar lines, let's do the same for this three-phase synchronous generator. So if we apply KVL between the between the ground point and go all the way till the positive terminal of VA, what we would observe is that VA, or basically let me rewrite it again, EA would be equal to, or other way around, VA would be equal to internal EMF minus the voltage drop across the armature's impedance. Let me mark it as at ZS, which is a synchronous impedance, minus IN into Zn, where IN Zn is the voltage drop across the neutral impedance, and IN is nothing but the sum of the corresponding phase currents as per KCL on the neutral point. Similarly, we would also have equation for phase B and phase C correspondingly. So EB EC minus IB ZS, IC ZS minus IN Zn, where we can expand IN in terms of individual phases. So if we compactly represent this in a vector form, this is what that vector form would look like. The three-phase voltages, they are functions of the internal EMF's phase voltage and the corresponding voltage drops across the self-impedance Zs and the neutral impedance Zn in terms of IA, IB, IC. And remember or recollect that VA, VB, VC was essentially equal to A times of VA 0, 1, 2, assuming phase A as reference for sequence components. So basically we have reference in phasor domain, we have also a reference of phase in defining which sequence component which we are trying to sort of represent. So we are assuming inherently phase A sequence components to be uniquely representing all other phase quantities. And on similar lines, this three-phase vector is also A times of IA 0, 1, 2, again assuming phase A as a reference for sequence components. So what I'm trying to basically do, the way we did it for sequence impedances of a three-phase balanced load, I'm trying to apply the same logic here with the underline or bottom part that EB, since EA, EB, EC are positive sequence voltages, EB is A square times of EA, and EC is A times of EA, where A was our complex operator, which is 1 at an angle 120 degrees. So dimensionless quantity, all in per units. So A is that same operator which is appearing in this term. So if we do that mathematical rearrangement, try to shift A from the LHS of VA012 to RHS, we can get the corresponding equations as shown here, and that's what internally I mentioned, that internal EMFs are assumed to be balanced. By balanced, I mean in terms of positive sequence voltages. So KVL equations, they would, rearranging the terms, would give us A inverse term here, A inverse and A. If we put in those multiplications as per the A matrix which we saw in the previous lecture, essentially this is one unique beautiful equation that we get, which in terms of sequence component states that VA0 as per this equation is equal to minus Z0. Let me see what is the notion of Z0 IA0. Then we have VA1 is equal to EA1 minus Z1 IA1. And lastly, VA2 is equal to minus Z2 IA2. What are EA1, Z0, Z1, Z2? Z0, Z1, Z2 are the respective 0, positive and negative sequence impedance of this loaded synchronous generator. So in terms of self-impedance and neutral impedance, Z0 is Zs plus 3 times of Zn. The neutral grounding aspect comes or influences the zero sequence impedance, as was also the case for transmission lines and for transformers. Z1 is equal to Z2, which is nothing but the synchronous impedance. For fault analysis, Zs would typically be the subtransient direct access reactance of the synchronous generator, with negligible resistance R being 0. So Zs refers to essentially J times of XD double dash, which is the subtransient direct access reactance in context of fault analysis. So that defines our sequence impedances, and EA1 is nothing but the internal EMF positive sequence voltage which is being generated in terms of phase A. Again, remember, when I talk about a three-phase system, if it is generating or if it is exactly equivalent to positive sequence voltage, then it is imperative that in this sort of a three-phase voltage arrangement, negative sequence and zero sequence components won't exist at all. VA0, VA2, they would all be 0 because inherently the generator is producing positive sequence voltage, so only the positive sequence component would come in. So in that context, since EA1 is positive sequence voltage, that is the reason why there is no voltage source appearing in the zero sequence and the negative sequence circuit. So if we were to redraw these or sort of represent these equations in terms of some fictitious circuit, those three circuits would look like as shown in this particular slide, slide number 5. Positive sequence circuit essentially consists of only the internal EMF, which is equal to EA1, with a voltage drop across the positive sequence impedance, and remaining negative sequence and zero sequence circuits, they are always passive circuits for a balanced three-phase synchronous generator. And these circuits, as can be seen, they are all essentially independent of each other. Once we know the positive sequence impedance, negative sequence and zero sequence impedance, which are functions of the machine synchronous impedances and neutral impedances, the resulting sequence circuits, they become completely independent, and that is where the beauty of Fortescue's theorem come in. Each of these circuits can be analyzed as per KVL, KCL independently without negative sequence current interfering with positive sequence or negative sequence voltage. Only the positive sequence network here has a voltage source, it's an active circuit, while the negative and zero sequence circuits are passive. And if we focus on this particular positive sequence circuit, we have already seen such a circuit for a three-phase balanced cylindrical pole synchronous generator, which was being represented by its analogous equivalent single-phase diagram. So if the machine operates under balanced condition, the same circuit is also used to analyze its steady state performance. The difference in that circuit would be that instead of direct access transient reactance, you would be using the steady state reactance. For positive and negative sequence circuits, the reference with which this terminal voltages are being measured is always the neutral point, whereas for zero sequence circuit, the zero sequence voltage is being measured with respect to ground. So in case the neutral and ground are not connected to each other, what would happen? If neutral and ground are not connected, let me go back to the circuit here. That means if there is a break between neutral and ground point, it is analogous equivalent to having neutral impedance as infinity. If neutral impedance is infinity, the zero sequence impedance would also be extremely high, and that's the reason why there would not be any flow of zero sequence current for the zero sequence network or circuit if neutral and ground are not connected. And that's the reason why for zero sequence network, ground acts as a reference for measurement of potential, specifically the zero sequence voltage, whereas for positive and negative sequence, neutral is the reference for measuring the voltages. If neutral and ground are unconnected, there is no flow of zero sequence current, because in that condition, Z0 tends to be infinity, which would indicate that no matter what the voltage source is, the corresponding current would always be zero. So that is the big difference in terms of sequence networks or components for synchronous generator. I hope all my viewers are comfortable so far with the understanding that we have developed. In case there is any confusion, please revisit the previous lecture slides that we have discussed so far. The next set of slides, as I mentioned in the beginning of today's discussion, we will start with our first unbalanced fault, which is also SLG, known as SLG fault. In sort of full form, it is single line to ground fault, also called as phase to ground fault. So we'll take up these unbalanced faults one by one, and to keep the discussion simple, we will focus only on generators per se. We won't be discussing the occurrence of these faults on the actual power network, although there is no necessity that these faults would always occur near the generator buses. Faults can occur elsewhere in the network also. So in the next lecture, hopefully I'll be able to convince all my viewers of how to understand these unbalanced faults occurrences elsewhere in the network, which is where the Thevenin theorem's application would come in. So the first single line to ground fault that we focus on is a phase A to ground fault, which has occurred at the terminal of the generator, the same generator, synchronous generator that we discussed in the previous few slides. There can be other possibilities of faults also, like single line to ground fault. It can happen between phase A and ground. It can also happen between phase B and ground. It can also happen between phase C and ground. Whatever we would discuss for phase A to ground, similar analogy would be applicable for other two single line to ground faults also. That is point number one. Point number two, since the fault has occurred at the generator terminal between phase A to ground, for simplicity, we are assuming the mutual impedance between the synchronous impedances of the per phase synchronous impedances of the synchronous generator. We are assuming the mutual impedance to be zero. Although if you consider mutual impedance as non-zero, what would happen? The circuit analogy would remain the same. Only the values of Z0, Z1 and Z2, they would change. Change in what context? On similar lines, the way mutually coupled three-phase balanced load sequence impedances were obtained in the previous lecture. So Zm is equal to 0 we are considering for the time being, but you can consider Zm to be non-zero also. The circuit analogy will remain the same. And to start with, we are assuming the generator is unloaded. In the unloaded sequence, so basically in the unloaded sense, the phase currents are all zero. The internal EMF are appearing at the phase voltage themselves. ZF is the fault impedance, and since a fault has occurred between phase A to ground, so if I apply KVL across this fault impedance, I would have VA is equal to IA ZF, and IA itself is the fault current, so IF represents the fault current, and since the generator is unloaded, the other phase currents, they don't exist. So the obvious question would come, oh, what would be the situation in case the phase currents are not zero, in case the generator is loaded? The answer to this we have indirectly discussed already in the balanced fault example that we discussed, that typically the impact of a fault always has a significance that the current tends to go up much more larger compared to normal load current. So even if the generator is loaded, the increase in fault current would be so great that compared to the fault current in phase A, IB and IC would be very, very small. So even a generator is loaded, due to fault, current in phase A will be several times larger, maybe 4, 5, 10 times larger than the other phase current, because the low impedance path offered across ZF, and hence it makes sense to have other phase currents to be zero even during the loaded condition. So with these two as our equations of understanding or importance, what is the purpose of understanding or analyzing this single line to ground fault? The purpose remains the same. Our objective is to find the fault current in terms of the known quantities. Now, these known quantities, what are they? They are the synchronous impedance of generator, fault impedance, terminal voltage, and so on. But we also have to see that, okay, for single line to ground fault, one could argue, oh, if VA is known and the fault impedance is known, then the analysis is nothing. It's just simple KVL application. But then the corresponding analysis, when it is done from the Thevenin's theorem perspective, becomes completely different. And that's where I gave a word of caution that at the outset, this understanding may appear to be very simple, but if the same fault were to occur in elsewhere position in the network, like on a transformer terminal or a bus terminal, where these quantities may be known, may not be known, then the understanding becomes very difficult, and hence the Thevenin's application would come in. So our objective, as I repeat again, our objective is to find IF in terms of certain known quantities. So let's apply Fortescue's theorem, and for phase A to ground fault specifically, I'll choose phase A as reference for sequence component. Phase A as a reference for sequence component. You could question or again argue in this, why not phase B, why not phase C? Please have patience, I'll come back to this point in the next few minutes probably. So I'm choosing phase A as my reference for sequence components, and if I recollect the phase B, phase C currents in terms of the sequence components, so what do you need to remember? You just have to remember the sequence of phasors for positive sequence. For positive sequence, if IA1 is, let's say, the reference, then IB1 is 120 degrees lagging phase A, and IC1 is leading by 120 degrees IA1. This is I120 degrees. This is for positive sequence. So the orientation here is ABC in the clockwise fashion. For negative sequence, the same sequence, the same phasors with similar magnitudes or maybe a different magnitudes can exist. But the sequence here is different. Here I have IA2, IC2 and IB2. This is 120. This is also 120. The sequence is ACB in clockwise fashion. This is a negative sequence. And for zero sequence, all the phasors, they are parallel to each other, IA0, IB0 and IC0 with the same magnitude. Here the magnitudes are same, they may be different in different systems. So if I just remember this, then I can always rewrite IB as IB0 plus IB1 plus IB2. And since I have chosen phase A as a reference for sequence components, I need to represent IB1 in terms of IA1, IB2 in terms of IA2, and IB0 in terms of IA0. For zero sequence components, the quantums are same, so there is no need of that A operator. Here, small a is the A's which we are seeing here. The small a is at an angle 120 degrees, and IB1, it is sort of lagging IA1 by 120 degrees. So if A is 1 at an angle 120 degrees, A square is 1 at an angle 240 degrees, which is also equal to A conjugate, which is 1 at an angle minus 120 degrees. And that's the reason why you have A square representing IB1 and similarly here this is representing IB2, and same goes for phase C current. So if I apply this coherency, IA0 gets cancelled. A square is not equal to A as shown over here. So the only possibility for this to happen is the positive sequence current and negative sequence currents are equal. Furthermore, IB is 0. So if I apply the expansion of IB in terms of phase currents, I also see that the zero sequence current happens to be same as the positive and negative sequence currents. Now, in what condition do you expect this condition to be true, where three distinct currents pertaining to three distinct circuits, those currents are as shown here. Under what condition can these three currents be equal? This is possible only when these sequence circuits, they are connected in series, and that is the inference that comes out from this, that the sequence currents are equal, which is possible only when the associated positive, negative and zero sequence component or circuit of this loaded, unloaded synchronous generator at the terminal of which phase A to ground fault has occurred are connected in series. So in terms of fault current IF, if I know what is the zero sequence current, I can also find what is the corresponding fault current. And if I apply the second logic, which was the KVL voltage VA in terms of IA ZF, since phase A is a reference, I can represent VA as VA0, VA1, VA2, and remember VA0 was the voltage drop, negative voltage drop across zero sequence impedance. VA1 was this term as per the sequence network of generator, and VA2 is this particular term, which is the negative sequence voltage drop with a negative sign. So if I put in those numbers, and since all the sequence currents are equal, so I can have an expression of fault current evaluation in terms of the internal EMF of generator and the corresponding known quantities of the corresponding fault impedances. Now, if you recollect or compare, the basic KVL equation which we started with was VA is equal to IA ZF, and the other expression of IF which we are getting in terms of fault impedance is EA1 and functions of Z0, Z1, Z2 and ZF. These two expressions are completely distinct. Reason? We are trying to find the worst case fault current, not the steady state current. And during faults, the maximum worst case fault current would appear only in the subtransient period. In subtransient period, having information of VA itself would be a big question mark. So essentially that's the reason why you are representing generators as internal EMF source with subtransient direct axis reactance, and that helps us in evaluating what is the IF worst case fault current in terms of the known quantities which are easily recognizable in fault analysis. So with these two concepts, concept number 1 and the equation of current that we have obtained, if we combine these two concepts and try to represent it over a circuit, this is the circuit that would look like. This 3ZF representation is coming in because 3ZF is term coming in over here. So for single line to ground fault, the respective, in case we have to understand single line to ground fault, phase A to ground fault specifically for fault occurring elsewhere in the network, which we will again discuss in the next lecture. Instead of having Z1, Z2, Z0 for the generator, we will make use of Thevenin's theorem to find the Thevenin impedances, and Z1, Z2, Z0 would be replaced by these Thevenin impedances, which we will again see in the next lecture. In case the generator is ungrounded, as I mentioned, the neutral impedance would be infinite and hence there would be no fault current at all. If Zn is infinity, Z0 is infinity, and you relook this expression, the value of fault current is undefined, because division by infinity is undefined. That means single line to ground fault will have no effect in an ungrounded system. If the generator is grounded through some impedance, that in that condition only single line to ground fault will have a implication. So in a way to restate it, and it may go a little offbeat, but then DC microgrids, which are alternative forms of small microgrids with DC sources and DC loads and few underground or underground cables mostly. DC microgrids, they are intently not grounded. They are intently not grounded to ensure that in case a single line to ground fault, or like pole to ground fault or pole to pole fault, pole to ground fault specifically, if it occurs in DC microgrid, Since the system is ungrounded, the single line to ground fault will have no fault current contribution. Reason? Because of this particular concept. And that's the reason why first line to ground fault or single line to ground fault in DC microgrid is not catastrophic. But the moment the next single line to ground fault occurs, Zn will no more be infinity because already there is a ground reference available and hence the fault currents would be very high. So some sort of interesting notion goes into those designing aspects of DC microgrid. Brings me to the end of single line to ground fault. Now there was a question which I raised up that why did I choose phase A as a reference for A to ground fault? You can recalculate or redo this analysis choosing phase B as a reference. Choosing phase B as a reference for symmetric components, sequence components or symmetric components. Please redo that and verify. What you would observe is that the phase B choice as reference for sequence components, the expressions of as shown in concept number 2, it will still be applicable. But concept number 1 will not be physically realizable in the sense, if you choose phase B as a reference for sequence components, what you would observe is that IB0 would be A times of IB1 and IB2 would be A square times of IB1. In case of phase A as a reference for sequence components, we had got all the sequence currents to be equal. If we choose phase B as a reference, we are still getting some correspondence between the sequence currents, but then the complex operator A is appearing in between. And that's the reason why concept number 1 physically won't be realizable. If concept number 1 is not physically realizable, representing this circuit won't be feasible or possible. That's the reason why there is a convention which goes by in single line to ground fault, that if phase A fault has occurred, please choose phase A as a reference. If phase B fault has occurred, choose phase B as a reference. And similarly, phase C to ground fault has occurred, please choose phase C as a reference. You'd be able to physically realize this circuit and have concept 1 also true. So that is the reason, please verify that. We'll conclude this discussion with double line to ground fault, where we have chosen a similar generator, but now we choose phase B and phase C as our faulty phases, shorted by impedance ZF. Phase A is healthy, so phase A current is almost 0 because the load current is very, very small compared to fault current, and if a generator is unloaded, phase A itself would be 0. By KVL across phase B and phase C, we have one equation, and then the other equation is that the fault current is IB or negative of IC. So we choose phase A as a reference again for sequence components for phase B to C fault. If we apply phase A as a reference, we see that 0 sequence current is perfectly 0 because IA is 0 and IB is negative of IC. So there is no 0 sequence network involved. Phase positive sequence currents and negative sequence currents, they are negative of each other. This is possible only when positive and negative sequence circuits are connected in anti-series fashion with 0 sequence open circuited. And if we represent our phase currents in terms of sequence current, this is the expression for the fault current, which we still have to find in terms of the internal EMF. So if we apply the KVL equation now, we get our fault current as IA1, IA2 in terms of this equation, where IA is 0, and this is the physical realizable circuit which represents how phase-to-phase fault circuit would look like in sequence network impedances. In case the fault occurs elsewhere in the network, we would make use of Thevenin impedances instead of Z1 and Z2, and since there is no ground appearing here, there is no notion of 0 sequence circuit important here. So phase-to-phase faults, they don't get affected by grounding. The neutral may be solidly grounded or may be open, so phase-to-phase faults will remain unaffected. So to summarize, for phase B to C fault, the reference that you have to choose is phase A for sequence components. If you have a phase C to A fault, you should choose phase B as a reference. If you have phase A to B fault, you have to choose phase C as a reference for sequence components. If you choose any other reference, this physical circuit representation of sequence networks won't be applicable, although the expression of currents, they would remain more or less similar. So the way we discussed for single line to ground fault, the same logic applies here. With this, I conclude my today's discussion. The next lecture will continue this for double line to ground faults and understanding Thevenin's theorem for the fault elsewhere in the network. Thank you.